Can I use? Oh, this one not.
Oh,
Maybe
here.
I see. Okay, yeah. Okay, that's good.
Okay, I think everyone is here, so let's get started. So just an announcement. So we're gonna take a photo after the second talk. So like right before lunch. So please don't be late. We're gonna take a photo first and then this. Yeah. So today it's a thermalization loop. So we have Tomotaka who's gonna tell us about quantum complexity and generalized area line fully connected.
Thank you for your introduction. My name is Tomotaka Kuwahara. My affiliation is RQC is maybe Research Center for Quantum Computing also. Yeah, and it's a great pleasure for me to have this opportunity to talk to you about my work. The presentation title is Quantum Complexity and Generalized Area Law in Free Connected Models. Sorry, today's topic is on the ground state instead of the quantum dynamics, but yeah, please allow me. And this work is a joint work with Dong-Hong Kim in RQC, and this work was uploaded in arXiv in 2024 and presented in QIP 2025. Today's main message is these two ones. The first one is area law holds without geometric structures. Usually the area law is considered for geometrical local system, but now I show the free connected model without geometric structure. But in that cases, we can prove the area law-like behaviors for entanglement entropies. The second message is the local Hamiltonian problem conjecture. LHP conjecture is almost true for fully connected models. I've explained the local Hamiltonian problem and LHP conjecture in the subsequent slides. Okay, so I start from the standard introduction, the area law conjectures, including the local Hamiltonian problems. And I also show the motivation to introduce a generalized area law on infinite dimensional graphs. Okay, so as a very simple setup, let's consider the Hamiltonians of the K-local forms. The K-local Hamiltonian is defined by the Hamiltonian which includes the interactions which involve at-most k spins. For example, in this picture, I consider the case that the three spins interact with each other. So in this case, Hz is defined on three spins, so Z is equal to the K is equal to 3. And in typical quantum systems, the two local Hamiltonian is considered in that case, K is equal to 2. And the most basic problem in quantum many-body physics is to solve the eigenproblem of the Hamiltonians. Of course, maybe as you know very well, the n-spin systems, for example, cubic systems, have exponentially large Hilbert space dimensions. So it's quite difficult to solve the eigenproblem, even for very simple models. For example, the Haldane conjecture, famous Haldane conjecture was defined for the simple Heisenberg model on one-dimensional chains. Oh, sorry. In here, to have spin system considered, but in this talk, I don't consider the I don't focus on the qubit system, but the QDIT general spin systems. Okay, sorry. And the local Hamiltonian problem is defined in this context, and in the very roughly speaking, the local Hamiltonian problem asks whether the ground energy is defined on some small energy windows. Here, the alpha and alpha plus zeta is considered, and zeta is the window of the energies. And our task is to decide whether the ground energy is included in these energy windows. And the very famous result by Kita F shows that this local Hamiltonian problem is QMA complete as long as the energy window size is as small as 1 over poly n. And QMA is very difficult problem, which is a quantum analog of NP. So QMA complete problem is almost impossible to solve efficiently, even by quantum computers. But this case is considered for generic Hamiltonian. So in other words, this considered the worst case So if we consider the more natural cases, for example, with physically natural cases, in that case, we can establish some more efficient approximation schemes or the good description of the quantum ground state. And in this context, the Ball conjecture, the local Hamiltonian problem, or the LHP conjecture was defined in this form. If the ground state is gapped, the gap means that the ground state and the first excited state have a one order omega one, I mean that's larger than some constant, which is independent of the system size, energy differences. And in that case, the complexity class of the LHP is as easy as the classical cases. So in 1D case, the difficulties are sort of the complexities in class P, and in higher dimensional cases, the complexity is classified into NP class. And gapped cases usually correspond to non-critical cases, and it determines the quantum phase of matter. So this kind of gapped ground state is one of the most important classes in condensed matter physics. Okay, so, and the current progress on the LHP conjecture is only for the 1D case. The 1D case, the area law was proven by Hastings in 2007, and by using these tasks, the classical simulation of a given ground state was completely solved in the case of 1D. The celebrated paper by Landau, Vajrayana, and Vidic. But in higher dimensional systems, the problem is widely open. And in that conjecture, the entanglement structure of the ground state plays a key role. And for this, for the characterization of the entanglement structures, the entanglement area law is considered. Here, we are interested in the entanglement amount of the entanglement when we bipartition a total system to A and B. And then we want to know how much entanglement exists. And here, I consider the Schmidt decomposition of some given quantum state, and the entanglement entropy is given by this form. Then the area law implies that the total amount of entanglement is upper bounded by some constant times the boundary area of the subsystems. So instead of the trivial upper bound that the entanglement entropy is proportional to volume, the entanglement area law means that the entanglement is proportional to the surface region of the boundaries. And in particular, if we consider 1D systems, the boundary size is order 1. So the entanglement, the area law of the entanglement implies that the entanglement entropy is upper bounded by some constant. Okay, and area law conjecture argues in which cases this kind of area law structure is true for the ground state. And the area law conjecture says that if the ground state is gapped or is in the non-critical phases, the area law is true for arbitrary quantum many-body systems. So entanglement entropy is at most at order of the surface region of the subsystem size. Here the gap definition is here. And the area law conjecture is now only proven for 1D systems. And the first proof, okay. The first proof was given by Hastings in 2007. And why? Okay. Maybe this one.
Maybe.
I see. Okay, good. And many of the generalization and improvement of the original Hastings proof was given. For example, including long-range interacting systems and long-range interacting bosonic systems, which have unbounded energies, local energies. However, in high-dimensional cases, even the proof of the sub-volume law instead of the area law is still very challenging. And so far, only the conditional proof was given. And our conditional proof means that in the original area law conjecture, we only assume the ground state is gapped, but conditional proof implies that in addition to the gap of the ground state, we assume some other non-trivial conditions. And I say that this one is a conditional proofs. For example, if we assume the adiabatic path from the trivially area law state to the target quantum state, then under the adiabatic assumption of the existence of adiabatic path, we can prove the entanglement area law in arbitrary dimensional systems. But of course, in that this proof is not the complete proof of the area law conjecture because we cannot prove the existence of adiabatic path. So in that sense, this area 2D high dimensional area law is still open. Yeah. Okay. And I also show why the area law is important. The area law is a necessary condition of the tensor network representations. The tensor network representation is some kind of efficient classical description of the quantum state. And when the ground state is efficiently described by tensor network formalism, then one can easily prove that the ground state satisfies entanglement area laws. So by taking the control positions, if we can say that if the entanglement area law breaks down, then the ground state cannot be efficiently described by tensor network. So the breakdown of the area law implies that all the algorithm and the classification based on the tensor network also breaks down. So area law is regarded as a cornerstone in recent modern physics. And we can say that the entanglement area law is a necessary condition, but it is also worth to note that the entanglement area law is not the sufficient conditions. So even if we could prove the entanglement area law conjecture for gapped ground state, but the efficient description of the tensor network of the gapped ground state is an even more difficult problem. Yeah. So in this sense, the area law conjecture is the first step to access to the LHP conjecture, but the LHP conjecture is furthermore difficult questions. Okay, from now, I want to go to the generalized area law. In the entanglement area law, the entanglement between the subsystem is only proportional to the surface regions. So we can consider more abstract setup. For example, the four-body QID systems, the QID A0 and small a, small b, and the capital B0. And in these four-body systems, the more generalized area law implies that entanglement entropy in this system is the proportional log of the boundary region. Boundary region is now defined by small a and small b. And our question is whether we can generalize area law conjecture to this setup. So we consider the four-body Hamiltonians and the ground state is gapped. In that case, we want to ask whether the entanglement entropy is proportional to like this form. And very interestingly, we can prove this conjecture for thermal equilibrium state. So thermal area law holds in this setup. And we can also prove the dynamical area law. The dynamical area law means that the entanglement rate is, the entanglement entropy generated by the time evolution is proportional to the surface area, now small a and small b. And this kind of dynamic area law is also proved for general four-body systems. So in this sense, the thermal equilibrium and the dynamical systems satisfy the generalized area law. But unfortunately, we know that the ground state area law does not hold in this generalized setup. There exists some counterexample, even though the small a and small b is given by QID. Maybe I remember that the dimension is 3, but the total entanglement entropy is as large as the total system, log of the total system Hilbert space dimensions. So in this sense, generalized area law is not true in general. Also, in the general quantum systems. Okay. Oh, sorry. Oh, sorry. This one? Oh, sorry. The small dA means the Hilbert space dimension of the QID small a, and dB means the Hilbert space dimension of the QID dB. And generalized area law implies that the log of this one, the generalized area law implies that the entanglement entropy is proportional to this size. Sorry, yeah. So I should have defined, show the definition of small d and small db. Okay.
So your interaction just between large capital A and lowercase a and b.
Exactly, yes. So interaction exists, small a and capital A0, small a and small b and capital B0, yes. And in addition, we also assume that the interaction between small a and small b is bounded by some constant. Yeah. Okay, so, and we know that the generalized area law is not true in general, but we still have other questions in which classes of quantum states satisfy the generalized area law. And for this candidate, I consider the fully connected graphs. The fully connected graphs that all the qubits interact with each other and connected with each other. So this model is also known as the all-to-all interacting systems, and it includes, for example, Sherrington-Kirkpatrick model for spin graphs, and Lipkin-Meshkov-Glick model for cavity systems, and Sachdev-Yeh-Kitaev model for the black hole physics, and so on. And recent quantum computation, this kind of free connected or the all-to-all interacting models attract much attention. And the very good property of the free connected model is that the product state well approximates the ground energies. The approximation error is at most as a square root of n if the system is gapped. And even without gap, the error is not n to the power 1 over 3, but n to the power 2 over 3. Sorry. Yeah. So for arbitrary Hamiltonian, the approximation error is at most n to the power 2 over 3, which is proved by Brandel Harrow in 2013. So the product state will approximate the ground energy. Yeah. And in very recent results, the classical simulation, for example, for the partition function with the order of n epsilon errors, and DMRG algorithm was numerically verified to approximate the ground state very well. So from these studies, the free connected models is expected to have the simple structures in the ground state. And my purpose is to understand the rigorous complexity of these free connected models.
Sorry.
Oh, sorry?
When you say error, that's the energy, right?
This one?
Yeah.
Yes.
Why is it like small? I mean.
Oh, square root n is still large, but it is much smaller than the order n errors. Yeah. Usually, okay. That's good. And so our purpose is to understand the generalized area law in free connected models, but you easily get the question, there are no boundary in the free connected model because all the spins interact with each other. So there are no boundaries. In other words, the boundary is as large as the system size. So at first glance, we have no boundaries. But the point is that we effectively map the boundary interactions, and then considering the boundary interaction is, effectively mapped to a small size boundaries, then we can say that the free connected model is in some sense mapped to the four-body systems with small dimensional A and small dimensional B. And this kind of constant size boundary is characterized by small Schmidt rank of the boundary interactions. So from this small Schmidt rank, for example, if the small Schmidt rank is equal to order 1 constant, then we expect that the generalized area law is entanglement entropy is still constant even in the free connected models. And purpose of this talk is to rigorously prove this kind of generalized area law in the free connected models. And the second problem is efficient classical description of the gapped ground state. Okay, so I will show the main setup and the main result. As I have explained, the main target is the free connective models with small Schmidt ranks.
So you're talking about Schmidt ranks of the interaction.
Yeah, that's correct. Yeah, very roughly speaking, by considering the operator Schmidt decomposition, then if the operator Schmidt decomposition have small Schmidt rank, then we can say that the operator Schmidt rank is small. But
The minimal rank for the let's say MQ decomposition.
yes, exactly. Yeah, but of course, in
General Hamiltonian, wouldn't that be like maximum?
for example, if we oh, yeah. In general, for example, if we consider one-dimensional systems or the finite, I mean the short-range interacting systems, then yeah. But if we consider long-range interacting system, usually the Schmidt rank is large. So in fact, okay, so I will explain this point. Okay. Yeah, and the second point, the generalized ideal and matrix spot approximation. Okay, so I will show the main setup, the many-body Hamiltonians, and here for the simplicity, I consider two-body systems, but the result is generalized arbitrary K-body interactions. And as the important notations, I introduce the subset interaction like HAB. Here, this one picks up all the interactions between the site I in A and site I dash in B. And the ground state is denoted by the omega, and the spectral gap is given by the capital delta. Then the entanglement entropy is standard definition like this form. Okay, so, and the main assumption is a small Schmidt rank, and the small Schmidt rank is a bit, not correct approximation. Sorry. In fact, the small Schmidt rank itself was not assumed, but actually the decay of the Schmidt coefficient is assumed. Yeah. So we consider the subset interactions like this form. And then, as he said, we consider some operator Schmidt decompositions and like this form. And HAS and HBS is now one local. Then we can denote the coefficient JS. And now our assumption is that JS, the summation of JS is upper bounded by some constant G1 bar. And if the DH is order 1 constant, then of course this JS is also order 1. But even though the DH is very, very large, if the JS decays linearly, we can also say that the summation of the Schmidt coefficient is upper bounded. And this kind of structure makes a Hamiltonian, which is similar to constant size boundaries. For example, to consider this point, let's consider, for example, the LMG model, Lipkin-Meshkov-Crick model. This is the all-to-all interacting XY model. So this one is the XX interaction, and this one is the YY interactions. And because the all-to-all interaction system, so the renormalization of the N appears. And if we consider the arbitrary subset interactions, A and B, then this is decomposed like this form. So this Hamiltonian has the rank 2. So DH is equal to, so G1 bar is also JX plus JY. And in this way, so if we consider the uniform Hamiltonians, always the Schmidt rank is upper bounded by some order 1. So this condition is obtained. But even under the the non-uniform Hamiltonians, we can still consider the Hamiltonian such that this kind of linear decay of the Schmidt coefficient is obtained. And very...
already having, for instance, a separately two-dimensional lattice. So this rules out, for instance, that your connectivity is two dimensions?
Two dimension? Sorry, but maybe if we consider two-dimensional systems, then this condition, the assumption is including the 1 over n. So generally, if we consider n, so the G1 bar is very, very large. Yeah. And the very important point is whether this assumption includes the SYK models. And very unfortunately, our result does not imply the SYK. Because the SYK include this kind of randomness, and randomness and the denormalization factor is given by n to the power 3 over 2 instead of n to the power 3. So we can easily see that the SYK model does not satisfy this kind of conditions. So, but if we consider, for example, the disorder-free case without any, the randomness, then we can prove that the disorder-free SYK model satisfies this condition. And this kind of disorder-free SYK Hamiltonian will be given in the tomorrow or the next tomorrow's talk by Hosho Katsura. Yeah. I see. Okay, so this is a very big open question whether we can include the SYK model in our generalized area law setups. Okay. In fact, this model not, because this model, I think this model does not satisfy the gap. So in order to make the area law, generalized area law is satisfied, then we may add some local potentials also. Yeah. Oh, sorry.
G1 bar is doesn't indicate the success of the interaction. What is the condition on G1 bar on?
Oh, sorry. G1 bar is some constant which will be obtained from this one.
There's the boundary and some object boundary. Some of them and the some object boundary is the condition. What's the
This one G1 existence of G1 bar is the conditions, so assumptions. And if some Hamiltonian is given, then we can also calculate G1 bar. For example, in the case of the LMG model, we can prove that G1 bar is given by Jx plus Jy. So this G1 bar is determined by the explicit Hamiltonian structures. But in this talk, I assume that G1 bar is order 1. Yeah. And the main result is this one, the generalized entanglement law up to some polylog factors. This means the poly exponent is now given by alpha 1 plus alpha 2 log f G1 bar delta. And plus log D is the local Hilbert space dimension, and 2 is not so important parameters. And alpha 1 is very large. Alpha 2 is also very large. Yeah, so this gives at most, but anyway, this one is constant. So we get entanglement entropy is given by polylog form as long as delta is larger than some constant. And we have very important open question, the optimality of this one. Of course, quantitatively, this is no longer optimal, but our question is, this kind of polylog form is optimal or not? So even under some gapped ground state of the orthogonal interaction systems, whether we can get some explicit quantum ground state such that, for example, log n entanglement scaling is still an open problem. And as long as we try several interacting models, then numerical result indicates that the entanglement entropy is upper bounded by some constant instead of the polylog upper bound. So the very important open question is whether what is the optimal upper bound? The optimal bound may be constant upper bound or log n upper bound, and still polylog n type upper bound may be optimal. But this point is still open. And second result is the matrix product approximation of the gapped ground state. Now, in order to define the 1D chain, we label each of the site by 1, 2, 3, 4 in this picture up to 20. And then this line of the under these labels, we can construct the matrix product state, and we construct some omega d, which is MPS with a bond dimension d, and we can prove that in order to achieve the approximation error like delta, then the bond dimension D is given by quasi-polynomial form, like exponential log n to the power of log 1 over delta. So delta, as long as delta is order 1 constant, then the bond dimension is quasi-polynomial, like exponential polylog n. And MPS is classically simulatable by classical sorry. Okay, good. Sorry. Yeah. Okay. Yeah. MPS is classically simulatable by classical computer with up to d to the power of 3. So from this fact, we can partially justify the numerical success of the DMRG algorithm for all-to-all interacting system, for example, in the paper by Tyndall. And this also partially answers the LHP conjecture on the free connected models. I remind us that the LHP conjecture says that ground state is gapped, then the complexity of the LHP is as easy as the classical case. And 1D case, in the high dimensional cases, in the except 1D case, the class is in NP. And because we can prove that in order to achieve the in order to achieve the MPS approximation, then the bond dimension is quasi-polynomial. So we can say that the LHP conjecture of the dense graph is almost true. Almost means that we cannot prove the polynomial approximation of the ground state instead of the quasi-polynomial bond dimension approximation. So in this sense, we can only say the LHP conjecture is almost true on dense graph. Yeah. And of course, the very important open problem is that whether we can improve the result to polynomial form. If we can prove the polynomial bond dimension is enough to approximate the ground state, then we can also prove that the LHP conjecture is true for on the dense graph. Yes.
Okay, actually, can I also ask you about your notation of 1 over delta? The 1 over delta is, what is it? Did you say something about it?
Oh, delta is the approximation errors. So if we want to get the very large, small approximation, for example, 1 over poly n, then so in that case, exponential log n to the power log n. So this is even not the quasi-polynomial, but the very still close to the quasi-polynomial form. Okay, yeah. Yes, quasi-polynomial means that exponential polylog n. Yeah, this one, yes. Yes.
So all dimension you would get the similarly similar error in 1 over delta. Just you are talking about 1 dimension cases.
Oh, in this case, I consider the fully connected model, so there are no dimensions. But even in this case, we can utilize the 1D-like structures. Yes. Okay. And the main technique, oh, sorry.
You show that, so what you're saying here is you have an MPS and that approximate.
Yes.
And then you claim that this corresponding LHP problem is
yeah, for example, if we prove that the poly n bond dimension is enough to approximate the ground state, then we can prove that the ground state LHP is in NP. Because by using the MPS as a classical proof to check the LHP is true or not, to verify the LHP. But now the MPS bond dimension size is quasi-polynomial. So in order to verify the MPS, we require the quasi-polynomial computational time to verify the proof MPS is true. Certainly, proves the LHP. So in this sense, we cannot prove the NP class of the LHP conjecture on the gap dense graph. Yeah. Okay. So I will show the main technique. The main technique is the mean field renormalization group technique. This one, maybe some of you know very well on the mean field approximations. And the mean field approximation renormalization group is that, this kind of approximation schemes. And the very important point is we require the efficiency guaranteed renormalization group techniques. This is a very important point and very challenging point. Okay, so I first show the basic, the line of the MFRG technique without the efficiency guarantees. So at this point, I don't show any efficiency guarantee, and the efficiency guarantee will be discussed afterward. In the step one, I first consider the mean field approximations. The mean field approximation is, roughly speaking, the approximation by using the product state. So we approximate the ground state by using product state. And this product state is defined by using the Schmidt decomposition of each of the site I. For example, for each of the site I, we consider the Schmidt decomposition, and we adopt the quantum state with the largest Schmidt coefficient as the mean field state. So this state is defined by 0, and lambda 0 is the largest Schmidt coefficient. And now, already this computation of the mean field state is usually NP hard. So because of this point, NP hard or NP complete, I'm not sure. But anyway, the finding the mean field state is usually very, very difficult problem. So even if we can get the optimal form of the generalized area law and the MPS approximations, we cannot access to the we cannot go beyond the NP class to the P class. Okay. And now we have gotten the mean field state, mean field basis, 0 state. And so we then decompose the total system into the many blocks. Now the block is defined by LS. And each of the block size is n to the power 1 by 8. So the number of blocks is now given by n to the power 7 over 8. Now the block Hilbert space dimension is still sub-exponential large, like exponential of the c times n to the power 1 over 8. So this Hilbert space dimension cannot be treated efficiently. So we truncate the Hilbert space dimension to construct the renormalized basis. In this truncation of the Hilbert space, we only consider the at most z site deviate from the mean field state. For example, in this picture, only the 2 state, now the 3rd state and the 6th state, is deviate from the mean field state. And by considering all the patterns of the z sites that deviate from the mean field state, then the pattern of to pick up the z site is given by n to the power of z over 8. And each of the deviated z sites has the Hilbert space dimension like d to the power of z. So as long as the z is order 1 constant, then this is still poly n Hilbert space dimensions. So we utilize this renormalized QID with the poly n local Hilbert space dimension in the next step. And so by utilizing this kind of projection to the renormalized Hilbert space with a dimension poly n, we construct some projections to truncate the deviated spins at most z sites. And then we construct the renormalized Hamiltonian like this form. Then now each of the blocks constitute the renormalized QID. So the new QID interaction is characterized by the renormalized, the block interaction between the block LS and block LS dash. So this is given by so the new QID interaction is given by this form. Okay, and then we can construct a new renormalized Hamiltonian. So we repeat the same process. So the Hilbert space, the number of the QIDs, becomes the power of 7 over 8. So if initial system has the n QID, then after the first renormalization process, the total number of QID becomes n to the power 7 over 8. And after the second renormalization process, the number of QID becomes n to the power 49 over 64. And after S0 renormalization processes, the total number of the renormalized qubit is given by n to the power of 7 over 8 to the power of S0. And the renormalized qubit dimension is, after the first renormalization group, the number of qubit is, the Hilbert space dimension is given by d to the power of z, n to the power of z over 8. And now this is the renormalized qubit Hilbert space dimension. So after second renormalization process, then this appears as the Hilbert space dimension of the renormalized qubit. And by repeating this process, then the final renormalized, the Hilbert space dimension of the renormalized qubit is given by dn to the power of z to the power of s0. So by choosing S0 proportional to, for example, log n, then the system size becomes order 1. But the renormalized qubit Hilbert space dimension is given by dn to the power of polylog n. So this is desired dimensions. And the main technical challenge is how to get the efficiency guarantee for this truncation Z. So this is a very, very big challenge. And if we can prove the efficiency guarantee, for example, even by choosing Z as order 1 constant, but the error is sufficiently small, then we can prove the main result. Okay, so I will show the technical ingredient to prove the main result. And the first important ingredient is the robustness of the ground state in the gapped auto-interacting systems. To derive this result, we first utilize this variance gap trade-off inequality. The gap times the variance of arbitrary local operator on subsystem is upper bounded by some constant times the subsystem size. And by using this upper bound, we can prove that this robustness lemma for arbitrary local unitary operators, which preserves the local Schmidt basis. I mean, that robustness implies that for arbitrary local unitary operator is acting on the unitary gapped ground state, but the energy is almost the same. And this robustness constant is given by delta lob, which is proportional to square root of 1 over square root of n delta. And the conditions that preserve the Schmidt base imply this one.
What do you mean by variance operator?
Oh, variance operator means that this one is measured by the ground state. So if we consider the variance of operator AL in the gapped ground state, this inequality is satisfied. I mean, the expectation of AL square minus the expectation of AL of square, and by taking the square root. Not taking the square root, yeah.
I'm sorry, yeah, about the unitarity, is it still unique, the unitarity for the robustness?
Oh, so you mean this one?
Yeah.
This is unitary operators.
Is it required?
Oh, these conditions? Oh, yeah. If this condition breaks down, we can easily construct this. This is not completely breaks down. Yeah. And by using this robustness lemma, we can also prove that the ground state is locally disentangled in the sense that the maximum Schmidt coefficient is almost equal to 1, up to the error of 1 over square root of n. So only from this result, we can prove that the entanglement entropy of the total system is proportional to square root of n. But the problem is how to further improve the square root of n upper bound of the entanglement entropy to the polylog n forms. And for this purpose, we utilize the renormalization process. And the first important point is that if the block is sufficiently smaller than the square root of n, then the robustness lemma implies that the ground state is almost given by the product state, like in this block size L. So the projection onto this one is upper bounded like this form. And if the L is sufficiently smaller than square root of n, then this is almost equal to 0. So from this inequality, we can say that as long as the block size is smaller than 1 square root of n, then inside the block, the mean field approximation is still very good. So our problem is how to derive the probability distribution to observe the deviation from the mean field state. And this problem is equivalent to obtaining the probability distribution of this one local operator. This is a kind of deviation operator from the mean field basis. So, for example, if the ML is equal to 0, then all the quantum state is given by the mean field state. So ML is equal to 0. And if the ML is sufficiently large, then so many quantum states is deviated from the mean field state. And we can prove that as long as the subsystem size L is smaller than square root of n, then ground state omega approximately minimizing ML. So ML, the expectation of ML is approximately equal to 0. And for this kind of one local operators, one can prove the exponential concentration bound for arbitrary gapped ground state, but the variance is given by square root of L over delta. This one is good, but now the square root of L is as large as the power of the system size. So this variance is still very large. So our second challenging point is to refine this kind of concentration bound to the stronger decay like this form, L times the delta log 1 over 2 to observe eigenvalues of ML larger than Z. This condition means that more than these size should deviate from the mean field state. So this probability is now given by this form. And now delta log is proportional to 1 over square root of n. So the decay rate is given by this form. So by choosing the block size as n to the power of 1 over 8, then we can say that the decay rate is given by n to the power minus z over 8. So in order to achieve the 1 over poly n errors, z is order 1 is enough. Now we can prove that after the Hilbert space truncation, the ground state is preserved and gap is also preserved. But we still have very big problems. Denormalized interaction amplitude. After the denormalization, we should consider the block-block interaction as the new QID interactions. But usually the block-block interaction is upper bounded by like this form, the subsystem size L and subsystem size L dash over n. So after the denormalizations, we can observe the significant amplification of the QID interactions. So the very essential point is we have to suppress the amplifications. And very important technique is there exists some appropriate decomposition of the block-block Hamiltonians. The HL dash is decomposed to like this form, and H tilde L is one local Hamiltonian on subsystem L. L dash is one local Hamiltonian on the L dash, and delta H L dash only characterize spin-spin interactions. Then we can prove that this term is only proportional to z to the power of L over n. So because the number of denormalized QID now is given by n over L, so we have to rewrite this one like this form. And this one is the number of denormalized QID. So now the QID interaction after the denormalization is proportional to z over number of the denormalized QID. So the interaction amplification is at most z times instead of the block sizes. So this one is z is still, still the interaction increase exponentially, but the denormalization process only log n times. So after the log n times the denormalization process, the interaction amplification is at most log n. So this is not so important. Okay, so I summarize it. Oh, sorry.
So if you apply this idea to like 2D, 3D, higher dimensional geometrically local system,
yes,
does it satisfy the condition you assumed about interaction strengths?
This way? In fact, it is very important. It is very important that interaction is denormalized by 1 over n in the assumptions, but this condition is not satisfied in geometrically local system. So this point kills. This point makes big problems. Yeah.
So this result only work for really complete system.
So you mean?
Like auto interaction.
Yes. Auto interaction is quite important in this setup. Yes. But of course, we may consider some sufficiently high dimensional system. For example, the D is sufficient, like a D is equal to 100 or 200 or so. And in that case, the entanglement entropy upper bound may be obtained as a function of the local cube, the spatial dimension D. But this is the open problems. Yeah. Okay, so I will summarize the talk. The main motivation is the entanglement area law on the free connective models. And this one is also connected to the local Hamiltonian problems. And we have proved the generalized area law and MPS approximation like this form. From this upper bound, we can say that the LHP conjecture is almost true for free connective models. And we can also say that the non-critical ground state have quasi-polynomial complexities. And very big open problem, two big open problem is, can we remove the polylog factors? And we may get some constant upper bound of the entanglement entropy in free connective models. The second one is also related to the first one, but if we can prove the polynomial complexity, I mean, the D is given by poly n to get the delta is, for example, given by 1 over poly n, then we can also say that LHP conjecture is true for arbitrary ground state on dense graph. And these two open problems are very active research topic in this field. Okay, so thank you for listening. Okay.
So you said that you think that's okay. Yeah. So you said you think you can remove the. So do you think it's true that there's a constant upper bound to the entanglement entropy?
It's very difficult question. I first believe that log n is the optimal upper bound, but the numerical calculation suggests that constant upper bound may be optimal.
But for example, in the LNG model, is it a constant or?
Yes, LNG model is constant as long as the gap is.
Because the LNG has like two phases, no?
Yes. So if we don't assume the gap condition, then the log n upper bound is known. But
okay.
Yeah. But yes.
Okay. Can I challenge question about? Okay. About you have so far the non-critical ground state. How about the critical ground state?
Yeah, this is also a very good question. But as far only from this renormalization technique, the deltas, I mean, if the delta is 1 over, for example, poly n, then the upper bound becomes also order n. So the area of structure completely breaks down. So I believe that some kind of good structure may be proved for critical ground state, but it is completely open. Yeah.
Yeah. Also, you have the gap so far study on the gap case.
Yes. So yes. So it is very, very interesting if we can something on the critical ground state, but so far there are no mathematical tool to approach this problem. Yes.
Yeah, I had a question.
Okay.
So you had like two variance bounds, like one like very general one, and then the other one that used this like projection.
Yes, this one.
Like what is the point of using the second one? Yeah, so this is the general one.
Oh yes.
Yeah, and then you had like another one, like maybe like a next slide.
Yeah. This upper bound is general one for it is satisfied for arbitrary k local. But by using the structure of the Hamiltonian is given by the all-total interacting system, then we can prove this inequality. So the free connected condition is utilized here to, I mean, combining this one and this, yeah.
Okay, thanks.
So maybe you mentioned earlier, but do you assume the unique gap ground states?
Yes, so here I assume the uniqueness and non-degenerate gap ground state.
So, but what if you have degenerate ground states
Yeah.
above which you have a gap?
I believe that the same technique should be obtained. For example, as long as the gap, I mean, the degeneracy is, for example, order one. But if the degeneracy is, for example, one poly-n degeneracies, the problem is not so simple. Yeah, because even in the 1D cases, the poly-n degeneracies was difficult to treat. So, but the order one degeneracy was very easy to treat in the 1D case. So I also believe that the order one degeneracy will be also treated in this case, but there are no proof now. Yeah.
So I guess once I go beyond kind of finite dimensions, I could also consider things like kind of random regular graphs, which are a bit closer to one dimension in the sense that they don't have many loops in them. Is there anything known about these kind of questions on those kind of graphs?
Oh, you mean the general graphs case?
Well, some like random regular graph or some graph which is like locally tree-like, so you don't have like short loops or only few short loops.
Oh, I see. But the very important point is if we consider general graph, then this kind of 1/n coefficient does not appear. Yeah, if we consider arbitrary, for example, general tree-like graph, then the interaction strength on each of the vertex is given by some order one constant. And if we, making this interaction strength as small as 1/n, then we can also prove the same result for the tree-like graph. But in that case, we should impose some very strong magnetic field compared with the interaction strength. So I think the result is not so interesting. If we apply this result to the generic infinite dimensional graphs.
Yeah, I was more wondering whether the usual techniques that work in one dimension might work in those cases, or some adaptation of those.
You mean, so what in this case?
Never mind. I'll ask you after.
Okay, so in fact, I'm not so sure how to further generalize this alternative case to the more structures, but close to the I think the auto interacting cases satisfy the area law, but the structure case does not satisfy the area law. But we can consider the intermediate cases. Still the connection is very, very many. I mean, many connections exist, but still includes some structures. So intermediate case between a structured quantum system and the free connective model is important to investigate. But now we don't have any rigorous result on this point.
All right. Okay, so let's thank
Okay.
Tomotaka one more time.
Thank you very much.
And, we'll reconvene in 30 minutes.